Hello, I'm Dr. Linick, and this is the last in our series of videos on examining the quadratic functions. And in this particular program, we're going to take a look at a couple of application problems dealing with the quadratic function. And our goal here is to get you comfortable with seeing that the mathematics behind quadratic functions actually can be applied to different situations and things that we are interested in finding. Okay, so let's go ahead and take a look at this first problem here, this application problem. And this is actually one from the business area. It says the demand equation for a retail product follows the equation x is equal to 250 minus 5p, or we can rewrite that equation as p is equal to negative 0.2x plus 50, where p is the price of the product sold and x is the number of units sold. So the first form that I have it is if we want to do this where we have a price and we want to look at how many units we can sell under that price, that's our equation. But if we know the number of units and want to figure out the price per unit, then we can use the second equation. Now, just popped in here as we were talking about that, this last notation here that if the revenue function is given by r is equal to xp, we want to find the price that will maximize the revenue. So that's what's going to make this a problem that deals with the quadratic function, because we want to find a maximum. All right, and I want to note that those two equations that I have started off with here up on top, the x equation and the p equation, we will note that these two are actually this, and I want to emphasize this, that these are actually different forms of the same equation. Now, we want to look at this revenue equation pretty carefully, that r is equal to xp. So both the price and the number of units sold will determine our revenue, which makes sense, because if we have 10 products and we're going to sell them for $9 a piece, then 10 times 9 will give us $90. That'll be our revenue. Again, revenue is the amount of money you just directly take in from selling the product at a particular price. All right, so let's see how we can figure out the maximum revenue here. And so let's look at this solution here. And so I'm going to go back to the demand equation in terms of p, that p is equal to negative 0.2x plus 50. And I want you to notice here that we've put a restriction on the domain of x, that x is going to be the smallest value of x could be 0, the largest value of x could be 250. So x is greater than or equal to 0 and less than or equal to 250 units here. Okay, looking next, again, we want to keep in mind that p is the price and then x is the number of units sold. So we want to determine the revenue function because, again, we're trying to maximize revenue. Now, what's going to happen here, too, as we look at this particular function is I want to emphasize that we want to write this function r, the revenue, in terms of x. All right, so we want to write the revenue function in terms of x because we're going to maximize the revenue. We've got two variables in there. So notice what happens. We're going to form a composite function. So we're going to bring some other information in here that you've used in earlier discussions in the course, and that was the idea of a composite function. A lot of students say, well, when can I use a composite function? Well, here we go. We had a function, and really this function here is a function p, the price function p of x. We could have called that p of x is equal to the negative 0.2x plus 50. All right, so we're going to plug that equation and the equivalent here, the expression, in for p, and so that's what happened. And so we'll get r is equal to x times p, which is equal to x times, in parentheses, negative 0.2x plus 50, close parentheses. Now, I'm going to come up here and say, well, wait a minute. What next can I do this? I don't see it yet. How is this a quadratic function? Well, we're basically going to simply distribute the x through the parentheses. Okay, so we get negative 0.2x squared plus 50x. So right now we have a quadratic function. If we look at the general form, which is this will be in f of x is equal to ax squared plus bx plus c, here c is going to be equal to 0. All right, so there's no C term in there, which is still perfectly fine in dealing with a quadratic function here. And because as long as a is not 0, we're okay there. We have a quadratic function. All right, so now let's see what we need to do to figure this out. Okay, since it's a quadratic function, the vertex is the maximum. So we need to find the x-coordinate of the vertex in order to find the price that will maximize the revenue. All right, so we're going to come through here and we're going to go back and we're going to use our equation x is equal to minus b over 2a. That was the equation of the x-coordinate for the vertex. And so we're going to see that our a in this particular case is going to be equal to negative 0.2. Our b is going to be equal to 50. So we get negative 50 divided by 2 times negative 0.2. That comes out to be x is equal to 125. Now, stop. Right now, we've got to stop a minute. All right, so let's review what we did. We formed a composite function. Then we saw that that composite function, as we went along, we made that composite function into, expanded out into a quadratic function. Now, from the quadratic function, we said that if we're looking to maximize something, then the maximum point on the quadratic has to be the vertex. So we found the x-coordinate of the vertex. Now, the reason why I said stop a moment, we found x is equal to 125. Remember, back earlier, we said x could be any value between 0 and 250, inclusive of those endpoints. So we're going to stop and look and say, all right, x is 125. It fits in between those restrictions on the domain, so we're good to go. So we're going to say, all right, there's nothing wrong with this equation. We're good to go. If x was outside that range, then we'll say, wait a minute, time out here. Somebody gave us the wrong equation, or we solved something wrong. Let's check it and see that if it is truly a proper price equation or a proper revenue equation. Okay, let's go back and see how we finish up this problem. Okay, so what we're going to do is we want to find the price that maximizes the revenue. Now, in quadratic functions, typically what you would do with a quadratic function is you would say, okay, we're going to find the vertex. All right, so we're not going to do that here. We're going to do that here somewhat. We're not going to do that completely here, because what we need to do is find the value of x, because we want to find the price that maximizes the revenue. All right, so we're going to now take that value of x, and that's why I told you to stop, and we're going to take that value of x and we're going to bring it back up here to plug it into this price equation. All right, so the price is going to be equal to p equal to negative 0.2 times 125 plus 50. This turns out to be 25. And so therefore, the price of $25 will maximize the revenue. All right, so this means that you will get a quadratic that comes out and you have your maximum revenue in that quadratic. All right, if you'd like, go ahead and plug that 25 into this the revenue equation, and I'm going to let you do that, and you can see what you're going to get. So if you plug in 25 is equal to negative 0.2 times 25 squared plus 50 times 25, that would give you your maximum revenue, okay? And we'll let you plug that in and come out to see what you get, okay? And that might be something where you compare with your classmates and see if everybody gets the same answer to that question. And so what we've seen here with this particular problem is that we can find out and use quadratic functions to find answers to problems that we're looking at in the business world, as far as finding what price should we have to maximize our revenue. And again, we were given some equations here, and those equations are mathematical models and a little bit beyond the full scope of this course to form those types of equations. So you might take an accounting course or a economics course to find out how you can develop modeling equations for price and revenue fully for business. All right, let's take a look at another scenario here of a second application. A city building department requires a construction project to have a rectangular drainage pond with a depth of 3 feet. The perimeter of the rectangular drainage pond is to be 60 feet. What dimension will maximize the area footprint of the rectangular drainage pond, and what is this area? Okay, so here's the idea. I've got a blue rectangle here drawn, and so typically a lot of codes require different things to happen, and then particularly in the drainage of property. I had a friend of mine who was building an office, small little office, and he had a very small piece of property, and he had to build something such as this with a drainage pond, and so it was an important part of the project. All right, so what we want to remember here is a couple things. We want to remember that the formula for the area of a rectangle is that the length times the width, L times W, will give us the area of the rectangle. We also remember that the perimeter of the rectangle is going to be twice the length plus twice the width. So basically we're adding up all 4 sides. There'll be 2 lengths and 2 widths in there. So just a refresher to bring us through to the fact that we've got to rely on some formulas from geometry here in solving this problem. Okay, so we've got this problem that we want to look at. We've looked at brought up the 2 formulas here for the area and perimeter. And so now what we're going to do is go to the problem and look at what is important in the problem. And the first thing that's important in the problem that we come across is we come across this idea of this depth of 3 feet. And so we want to say, well, wait a minute. We're looking at a rectangular area. So we're not going to be concerned about the depth, because what we're going to have assumed here, this is kind of just extraneous information just thrown in to say, because in the drainage pond, the depth of 3 feet would go down, and that would be a volume. And we didn't talk about a volume here. We're really looking at just how you would set this pond up. So if you're looking at from an aerial shot, so to speak, what the area of that footprint would be on the property. So if you want a piece of paper. All right, so that piece of information, we can say, well, we don't really need that right now. And so what's really important is that the pond is to be 60 feet. Okay, so 60 feet there is the perimeter of the pond. All right, so the whole perimeter of the pond, it has to be 60 feet. So you'll see on your screen here, I've got 60 is equal to 2L plus 2W. So what we're going to do is we're going to first of all start out with the perimeter. Now that's not a quadratic equation right now. So you're saying, okay, it's a linear equation with 2 variables. Well, let's rewrite that equation, and so that we have L is equal to 30 minus W. And so basically what I did was I divided everything through by 2. So to solve this, I divide by 2, I get 30 is equal to L plus W, and then I subtracted W from both sides of the equation. All right, and I end up with L is equal to 30 minus W. Now, how's that going to help me? Well, notice that in my area equation, I have both length and width, and so we really like to rewrite this in terms of one of the variables. In this particular case, I've chosen to rewrite the area as a function in terms of the width. So A is equal to, A of W, A of the width, is equal to 30 minus W times W. Okay, so this 30 minus W, again, was our length. All right, so now we're going to see where the quadratic portion of it comes in. So what we're going to do is we're going to come up here and we're going to say, okay, this is going to be equal to what? 30W minus W squared. Again, I'm going to distribute my variable through there, my variable of W through there, and we'll get 30 minus W squared here. All right, so now we have a quadratic function of the area in terms of the width. All right, so what we want to do is we want to solve this little problem here, and make that W look a little nicer there for us all. Okay, so we have our W's there. All right, and so what we're going to do is, again, we're looking at the idea of maximizing this footprint. All right, so the maximum occurs at, again, your vertex. And so what we're going to do is we're going to use our formula that x is equal to minus b over 2a. Well, in this particular case, we're going to change it to w is equal to minus b over 2a because we want to solve for the width. All right, so we're going to see our b here is what? Our b is equal to 30, so be careful with that. b is equal to 30, and a is equal to minus 1. All right, so I'll have minus 30 over 2 times negative 1. That's going to give us then minus 30 over minus 2, which will give us 15. Now, we know, looking back, this was in terms of feet, so this will be 15 feet. So our width is going to be 15 feet. All right, so again, we're looking at what dimension will maximize this. Well, let's get the other dimension. Well, we're going to come down back over here to what L was equal to 30 minus W, and that's going to be equal to 30 minus 15. So we see the length is also going to be equal to 15 feet. So what we're going to have happen here is, instead of a nice rectangle, we'll actually have a square. Well, a square is a form of a rectangle, so we'll see we have a square will fit the bill here for what we need as this drainage pond. All right, and finally we're going to say, well, wait a minute. We want to find what that maximum area is going to be. So we're going to see that we're going to have the area is just going to be equal to what? 15 feet, which is our length, times 15 feet, which is our width. So our maximum area is going to be 225 square feet. All right, so again, we could have gone back up to our function and plugged in just w is equal to 15 into our function. We could have gotten that maximum area as well. All right, so, or we could have gone back to the area formula as I did here. And so what we see is that, in conclusion, that in this construction project, besides digging this drainage rectangular drainage pond down 3 feet, they have to have something that's 15 feet wide by 15 feet across, so a nice square there. And that'll end up with having a footprint on the flat there, so to speak, of the land of 225 square feet. So again, we've seen another application here, a second application of how we can solve or use the quadratic functions to solve application problems. Okay, this concludes our discussion of the quadratic functions. Please be sure to go back and review any of the programs as we went along. If there was something that you felt that you wanted to see again after you saw the application problems, to go back and review how we found the vertex and how we concluded that the vertex was our maximum. Thank you.